So Unit 5, Modern Physics, the next lecture is going to be on photons and the quantum theory of light. So we've talked about quantum theory a bit. I've introduced it to you. Now we're going to look at how do photons interact with this quantum theory. And of course photons are the kind of that particle of light. So we'll get into that discussion in this lecture. And I should mention, this is also section 12.2 from your textbook if you want to follow along. So in the early 1800s, Thomas Young performed his double slit experiment. And this double slit experiment, of course, showed that light behaves like a wave. Now, around the same time, Maxwell ended up developing his theory of electromagnetic waves, and physicists ended up getting this idea that light itself was an electromagnetic wave. So we had this connection between electromagnetic waves and light, this ended up causing people to understand or to think that the nature of light was well understood, and that within the next few hundred years or so, it would be fully solved on the physics of light. But by the end of the 1800s, some things were noticed that were kind of strange in terms of how they were happening, and they weren't explained readily with the idea of the understanding of the theory of light that they had at the time. So we'll get into some of those interactions that were not explained by the models of the time. So the one that we're going to focus on in this lecture actually is going to be when light was shown on on certain types of metals. Electrons were emitted from those metals. So the idea that how was light causing matter to move? So somehow this light, which was a wave, was causing matter, electrons, to jump off of metals, and this wasn't understood on how this would happen, because there had to be some sort of energy that was removing these electrons. So through experimentation, they found that the minimum amount of energy needed to emit an electron was 1.6 times 10 to the negative 19 joules. Now, looking at that number, you might find it's kind of familiar to you. If you recall, what is the elementary charge of an electron or a proton? And that charge is 1.6 times 10 to the negative 19 coulombs. Well, this work function ended up being 1.6 times 10 to the negative 19 joules. And it turns out that it was the energy required to have one electron be emitted from a metal plate was equal to the elementary charge. So this, while we give this in joules, another way of understanding this is in a unit of energy that you'll use a lot more in university than you will here, which is the electron volt. And 1 electron volt is the energy required to emit 1 electron. So this is what we call the work function of a metal. How much energy is needed to start emitting electrons. And you can measure the work function of a metal by applying an electric potential, a voltage, and the smallest electric potential difference that's able to emit electrons will give you the work function of the metal. So basically, in this image, what you see here is a metal sample, and we're applying a voltage difference, a potential difference between the metal sample and the metal plate. If we have a vacuum in between, which would essentially eliminate any other sources of interference, then what we'll have is when we set our potential difference to a certain value, the smallest possible value we can set it to, that will have one electron be emitted, works out to be the work function of that metal. So I'd like you to copy this slide down. It defines the work function, the minimum energy needed to remove an electron bound to a metal surface. We measure this in electron volts rather than joules because it's a little bit easier to understand in the sense that it's going to be very small measures of joules, but the electron volt itself would be in the order of 10 to the power of 0 or 10 to the power of 1. W is, of course, our work function. E is the elementary charge of an electron. And delta V is our potential difference. 1 electron volt, of course, is 1.6 times 10 to the negative 19 joules. So let's try a problem. Here it says that we have a shiny metal. Its work function is unknown, and it's connected through a potential difference to another metal plate. When we end up setting that potential difference to 5.65 volts, electrons start to be emitted. The work function is equal to the elementary charge times the voltage difference. So our work function ends up being 1.6 times 10 to the negative 19 times our voltage, which is 5.65. So it is equal to 9.04 times 10 to the negative 19 joules. You can see that if I multiply here, 1.6 times 5.65, 9.04, and the 10 to the negative 19 will just be added to that or multiplied to that. But another way of writing this is simply just as 5.65 electron volts. So it kind of shows that it's a bit easier just to write the that voltage difference. And if we write it as electron volts, that is actually a unit of energy. And let's move on now to another part of this lecture. Just a second here, turn this off. So, another way to extract electrons from a metal is by shining a light onto it. So that was that's a way of determining the work function of a metal. So we know how much energy is needed to start emitting electrons. Now, the interesting thing is, this was what puzzled the physicists in the 1880s, was light could also emit electrons. So how is this possible? And what type of light how do we know, how could we start emitting electrons? I'm just redoing that. I'm waiting to think of my words, and I'm going to start again. So we understand the work function. That's how much voltage difference we need to start emitting electrons from a metal. But we know also that light can emit electrons as well. But the question is, how strong does the light have to be? What does its frequency have to be? How much energy does the light have to have in order to start emitting electrons? So this was what puzzled physicists in the 1880s, because at the understanding of light at that time, there was not there wasn't any sort of mechanism that would allow light to start emitting electrons. So this effect, which we call the photoelectric effect, was very interesting, and it was studied quite a lot. When we have an electron being emitted from a metal due to light, it's called the photoelectric effect. And the electron that's emitted is referred to as the photoelectron, or a photoelectron. And what experimental studies showed at the time was that there was a certain frequency that was required to start emitting electrons. This was called the threshold frequency. It was given the symbol F0 or F0, subscript 0. This was the minimum frequency that was required for electrons to start being ejected from the material. If you had light that was less than this frequency, no electrons would be emitted. But as soon as you hit this frequency, you'd start to have one electron emitted, and the more that you increase this frequency, you would have more electrons emitted. And as you can see from that small little image there, the plot, it is a linear relationship. So the greater the frequency increases, the more electrons are emitted, proportionally to that frequency. And this slide just explains what I said. It says that the greater the frequency, the kinetic energy of the emitted electrons varies linearly with the frequency. So it was the not only is there more electrons emitted, but the kinetic energy of the electrons actually increases as well. So they get ejected at a greater velocity. So physicists tried to explain why this photoelectric effect was happening using the classical wave theory of light. But there were two main problems with this. And the first was that that threshold frequency, the frequency required for electrons to start being emitted, was independent of the intensity of the light. So if we ended up increasing the intensity of the light, if you remember classical wave theory, that brightness of the light, the intensity, would be the amplitude. And with the greater amplitude, we have greater energy. So the idea was that if we have very bright light, we should be able to decrease the threshold frequency. And with dim light, we could still emit electrons, but it would be a greater threshold frequency. This was in fact not happening. So the classical wave theory of light, which was predicting that the intensity would increase or decrease the threshold frequency, was not happening. And the second part of this was that if we had a brighter light, it would have been understood that the ejected electrons, the photoelectrons, would have a greater kinetic energy. But this was actually not happening. So what was found was that whether the light was bright or dim, it was the ejected electrons would have the same kinetic energy. The kinetic energy was solely dependent on the frequency. So copy this down here. You'll need to explain this for tests. The photoelectric effect and why, what is it and why was it not explained well using the classical theory of light. So the phenomena, it's the phenomena of electrons being ejected from a material when exposed to light or electromagnetic radiation. It was not able to be explained using the classical wave theory of light. The reason why was that the threshold frequency was independent of the light intensity, and the kinetic energy of the photoelectrons is independent of the light intensity. Now that threshold frequency is the minimum frequency at which electrons are ejected from a material. That's another thing I'd like you to copy down. So here's a question. It says, a wavelength of dim red light ejects no electrons. Let's say we increase the intensity of those electrons, or of that light, by a factor of 1,000. Would it start to eject electrons? And the answer here is no, it would not, because the frequency of the red light would still be below that threshold frequency. So it doesn't matter how intense the light is. What we need to do is we need to, instead of using red light, we need to use light of a greater frequency. So 1905 comes around, and Albert Einstein ends up talking about light in a bit of a different way. And he says that light should be considered as a collection of particles called photons. Now, why was this strange? Well, we just went through the whole period of if you remember, even 300 years prior to this, we had Huygens and Newton were discussing what the nature of light was, and we were talking about, is it a particle or is it a wave? And it was first thought to be a particle, and then Young's experiment shows that light is a wave. So we were kind of moving away from this idea that light is a particle. But Albert Einstein comes around 1905 and he says, well, let's start looking at light as a particle. So this was really kind of confusing to people as well, because it was thought that we've already moved past this. But Einstein ends up bringing us back to this idea that light is a particle, and this is sort of the start of our wave-particle duality understanding of light. So he proposes these photons, which are particles of matter, but they're very different from the classical particles. So the photons that Albert Einstein starts to envision are particles of matter that do not have a mass, but they exhibit interference effects, just as electrons do in a double-slit interference experiment. And Einstein ends up saying that these photons carry a maximum kinetic energy in parcels, or quantum, and the amount of energy they carry is equal to h, which is Planck's constant, times F. And Planck's constant, I'd like to copy this note down. You'll study this more in university, but Planck's constant was it was a constant that was introduced by Max Planck to explain blackbody radiation, which is a property of incandescent objects, and it was sort of it was new at the time, but it's a measure of joules seconds. So it's the amount of energy time that we have in a photon, or rather in any sort of electromagnetic wave. So the way that Einstein thought of this was, if Planck's constant is something that we can use to measure how much energy we have in an electromagnetic wave, then the photons themselves carry this energy, and the photon energy is equal to Planck's constant times the frequency of the electromagnetic radiation. So to go through Max Planck's work a little bit here, this was in 1901, so a little bit before Einstein proposed the photon theory of light. Max Planck was studying blackbodies and blackbody radiation. And what a blackbody is, it's an object that absorbs all radiation that reaches it. So blackbody radiation is a radiation emitted by a blackbody. And you could think of a blackbody as something that is very, very, a very large heat source. So the sun, for example, is a blackbody. The radiation that goes into our sun does not get, it gets completely absorbed. But the sun emits a radiation. That's a type of blackbody radiation. On Earth, we can think of a kiln. So a kiln is a kind of like a furnace for burning, or for cooking ceramics in a way. It's really like a really high temperature oven. So the temperature of the kiln, as that temperature increases, the frequency that is emitted with the highest intensity becomes higher. So if you look at this curve that we have here, we have a, if you imagine different sort of heat curves. So we have a curve there with 6,000 Kelvin, another one with 3,000, another with 2,000. The frequency of the emitted light is dependent on the heat and the relative intensity. So you don't need to understand this very well because we don't actually study this in this course, but I just want to give you an understanding of what a black body is. But another way of thinking of it is if you heat up something and you make it really, really hot, it starts to light up. That's a type of black body radiation. It's actually usually it's a partial black body because it doesn't absorb everything, but that's a type of radiation that occurs when something is absorbing a lot of EM radiation. Now, why we do need to study it for this course is that there's a relationship between this and the photoelectric effect, and we'll get into that a little bit later. So at low frequencies, predictions based on the classical theory agree with the observed data for the intensity of radiation from a black body. At high frequencies, though, theory and observation diverge quite drastically. So the discrepancy between theory and observation shocked physicists of the day, and they call it the ultraviolet catastrophe. So this was the idea that classical physics would have predicted a forever increasing frequency of light as our intensity increases. But what was actually observed was that after a certain point, the light would start to, or the emitted light, or EM radiation, I should say, would start to die down, and you would have that kind of decrease in frequency of the light, so or decrease in the intensity of the light. So that was the ultraviolet catastrophe. And why was this happening? It wasn't very well understood. So Planck resolved this disagreement by hypothesizing that the energy in a black body comes in quanta, and that each parcel of energy has an energy equal to hf, where f is the frequency and h is that universal constant that he introduced. So his theory fit the experiments perfectly, but no one, not even Planck, knew why. Max Planck just introduced this constant and said, look, it works, I don't know why. And it took a few years. 1905, Einstein ends up answering that part and saying, well, it's because the energy, there's a mass particle, a photon, that is carrying that energy. So copy this slide down here. Photons are discrete bundles of energy carried by light. They do not have mass, but they exhibit interference effects. The energy of a photon is h times f, where h is Planck's constant. It could also be written as h equals c over lambda, where c is the speed of light, and lambda is, of course, the wavelength of the light. So you might want to pause to copy down those, the definitions of each of those terms. So Einstein's photon, or his quantum theory, explains the two puzzles associated with the photoelectric effect. So the first puzzle, of course, was that the intensity of the light, as we increase that intensity, we should see some sort of increase or decrease with the threshold frequency. But the absorption of light by an electron is actually a collision between a photon and an electron. So the photon's energy, which is hf, gets absorbed by the electron, and that energy, so when this energy is less than the work function, right, the electron is not able to escape the metal. So if it absorbs that energy, it becomes more excited, but it stays within the metal. The second part of this, that threshold frequency of the photoelectric effect, it corresponds to photons whose energy is equal to the work function. So if we have a photon, and if its energy, its hf, was equal to the work function of that metal, then we could start seeing electrons being ejected. But if it is less, the electrons do not leave the metal, they become more excited. If it's more, the electrons leave the metal with a greater kinetic energy. And there's a pretty simple equation for this. The kinetic energy of a photoelectron is equal to hf, which is the energy of the photon, minus HF naught, which is the energy of the work function. Or you can write this as EK equals HF minus W. And of course, this is a straight line equation where EK is directly proportional to the frequency. So now here's the other thing that Einstein sort of showed. If you graphed that linear equation, that simple linear equation, and you graphed it back to the y-axis, the intercept on the y-axis would actually be equal to the work function, although it would be a negative. So if we have a surface 1 here and its work function was W1, the distance between the y-intercept and 0 would be equal to the work function of surface 1. So this linear behavior is precisely what was found in the photoelectric experiments, and that slope could be used to find the work function as well. So that slope of each of those different surfaces is equal to h. It's equal to Planck's constant. So I'd like you to copy this picture down, and I'd like you to copy down that the slope is equal to h. And I'd like you to copy down that W1, W2, and W3 are equal to the individual work functions of each of those surfaces. So while Einstein's explanation could account for all of the observations of the photoelectric effect, there were very few physicists who accepted his argument. And the reason why was because he was going back to this, this particle theory of light that physicists were ready to move away from after Young's double slit experiment. So it was very difficult for physicists because they were thinking, well, you know, we were understanding light, but now Albert Einstein's putting in this whole new understanding, and it's got to change a lot of what we know. Over time, it started to become more embraced because it fully explained the photoelectric effect, and it was able to have other applications, which we'll get into as well. Peter Millikan, who you'll remember from Millikan's experiment where he measured the elementary charge, he ended up verifying Einstein's quantum theory of light. So here's a nice interaction between a theoretical physicist, Albert Einstein, and Peter Millikan, who is an experimental physicist. So the theoretical physicists, like Einstein, end up proposing the theories. The experimental physicists end up verifying those theories. So here is another slide to copy down on the photoelectric effect. Give you some time to copy this down, or you can pause and copy this down. I will make a comment. The note is very important as well. If the energy of the photon is less than the work function, the electron does not escape. If the energy of the photon is equal to the work function, the electron just escapes. Its kinetic energy, though, is 0. If the electron, or the kinetic energy, if the energy of the photon is greater than the work function, the electron escapes and its kinetic energy is greater than 0. So here's a question to practice. It says here, aluminum is being used in a photoelectric effect experiment, and the work function of aluminum is 6.73 times 10 to the negative 19 joules. It says calculate the minimum photon energy needed. So our minimum photon energy needed would be, if we write down our photoelectric effect, it's HF minus W. Our minimum energy needed can be found by setting the kinetic energy to 0. And of course, we know our work function, which is 6.73 times 10 to the negative 19. And then we just need to move this to the other side. And we need to find the minimum kinetic energy. Well, or the minimum energy needed is 6.73 times 10 to the negative 19 joules. And the frequency needed would be the 6.73 times 10 to the negative 19 over Planck's constant, which at the front of your formula sheet you should have Planck's constant at 6.63 times 10 to the negative 34. And this works out to 6.673 divided by 6.63. If we have to also multiply this by 10 to the negative 19 and divide by 10 to the power of negative 34, we end up with 1.02 times 10 to the 15 hertz. So the next part of this question, it says if we have blue light, which is of 450 nanometers, and it is incident on this, determine whether electrons are emitted, and if they are, determine the maximum kinetic energy. Well, the first thing we can do is figure out what's the energy of the photons of blue light. So that can be found by multiplying H times F, and our F here is 450 nano. Sorry, that's a wavelength, so we'll have to write this as C over lambda. So 6.63 times 10 to the negative 34 C over lambda, which is 450 nano. Sorry, it's really kind of small there. But here's what it will look like. 6.63 times 3 divided by 450 times 10 to the power of negative 34 times 10 to the power of 8 divided by 10 to the power of negative 9. And I'm left with 4.42, so my energy of my photon is 4.42 times 10 to the negative 9, 10 to the negative 19 rather, joules. Now since this energy is less than my work function energy, therefore no electrons emitted. So let's move on now to another question here. It says, when UV radiation is used to eject electrons from a metal surface, it says that the work function of this metal surface is 4.25 electron volts. The maximum kinetic energy of electrons emitted is 2.00 electron volts. So what was the frequency and the wavelength of the radiation used? So here, we start off again. It is the energy, the kinetic energy, is equal to HF minus W. And in this case, we'll leave things in electron volts. So it says our W is 4.25. It says the maximum kinetic energy is 2. So here, if we have 2.00 on this side, and if we have 4.25 here, that means that HF equals, I can just do this in my head, this is actually going to be 6.25 electron volts. Now my frequency can be found by dividing 6.25 by, what is this here? 6.63 times 10 to the negative 34. That's Planck's constant. And if I do this calculation, you'll see 6.25 divided by 6.63. Oops. I actually will have to change this into joules because electron volts don't work with Planck's constant. So to change this into joules, I have to also multiply by 1.6 times 10 to the negative 19. So times 1.6, and then this would be times 10 to the power of negative 19 divided by 10 to the power of negative 34. And we end up with 1.51 times 10 to the 10 to the 15 hertz. And we could change this into our wavelength, because the wavelength is going to be equal to, F equals C over lambda. Lambda equals F over C, no, CF. C over F, sorry. Lambda equals C over F. So if I just take this value here, I can reciprocate it, and then I can multiply it by C, which is 3 times 10 to the power of 8. And I end up with, I should write this in nanometers, so I'm going to write 199 nanometers. Okay, one more here. It says electrons emitted from a surface illuminated by light with wavelength of 460 have a maximum speed of 4.2 times 10 to the 5 meters per second. Given the electron has a mass of 9.11 times 10 to the negative 31, calculate the work function in joules and electron volts of the surface material. So here we have EK equals HF minus W. And our EK, our kinetic energy, can be found as 1/2 mv squared equals HF minus W. Now what I need to solve for is the work function, so rearranging this, I end up with W equals HF minus 1/2 mv squared. So W equals H, which is 6.63 times 10 to the negative 34. F, which is my frequency of my light. Well, I have it as a wavelength, so I'm going to rewrite this instead of this as F. I'm going to write it using H equals C over lambda. So C, which is 3.0 times 10 to the 8 over lambda, which is 460 times 10 to the negative 9. Minus 1/2 m, which is the mass of an electron, which is 9.11 times 10 to the negative 31, times the v squared, which is 4.2 times 10 to the 5 squared. So now all of this put in the calculator at once should give me my work function. So I'll do this: 6.63 times 10 to the negative 34 times 3 times 10 to the power of 8 divided by 460 divided by 10 to the power of negative 9 minus 0.5 times 9.11 times 10 to the power of negative 31 times 4.2 times 4.2 times 10 to the power of 10, because that's what 10 to the 5 squared is. It gets me to 3.5. I have to limit this to 2 significant digits because my speed was in 2 significant digits. 3.5 times 10 to the negative 19 joules. And then to get this as an electron volt value, I have to divide by 1.6 times 10 to the negative 19, which is just this divided by 1.6, and if again I divide by 10 to the negative 19, I should get 2.2 electron volts. Oops, electron volts, that's a V. So again, this was thought to have very few practical applications, but the photoelectric effect ended up being used to create light meters that measured the intensity of light. And you can kind of read this slide. It sort of explains how it works. Now, the photon, just to finish off, which was once something that was very difficult for people to understand. It's almost now well accepted, not only by physicists, but by people in general. So that's it for this lecture. I know it's been quite a bit of work for today, but try out the questions here. If you have any trouble, you can ask for help on our course website.